Okay, so here we are. This is day 2 of our Exponents and Logarithms unit. Today we're going to look at graphing and analyzing exponential functions. So our first example here, this is function notation. F of x is equal to 2 to the x, 2 to the power of x. So this is a basic exponential function. So we're going to look at graphing it to begin. And to do that, we can help ourselves out here by just creating a table of values. So I can select any value that I want for x. I'm going to pick values that are close to the point of origin. So let's go with -2, -1, 0, 1, and 2. Okay, and I'll just fill this in somewhat out of order. Let's think about if x is 0. So we've got 2 raised to the power of 0. 0 law tells us that this is equal to 1. 2 to the power of 1 is 2, and 2 squared is 4. Okay, now we've got negative values of x, so we got to think about negative exponents. Let's try -1 to begin. So 2 to the power of -1. The negative exponent tells us to flip the base or reciprocate the base. Reciprocal of 2 is 1 over 2. The exponent becomes positive, and so 2 to the power of -1 is 1/2. Okay, similarly, if we've got 2 to the power of -2, negative exponent tells us to reciprocate the base. That becomes 1 over 2. Exponent becomes positive, and so we get that 2 to the power of -2 is 1 over 4. Okay, so we've got 5 different points here that we can plot on our graph. So let's do that. -2 and 1 over 4, -1 and 1/2, 0 and 1, 1 and 2, 2 and 4. Okay, so here's the general shape here. It looks something like this. There we go. And so what you'll notice is that there is no value that we can plug in for x to produce a y value of 0 or a negative y value. So we don't see it, but we can say that there is a horizontal asymptote here at the x-axis, which is y equals 0. Okay, so asymptote is y equals 0. And what are some other features of this graph? Well, it's got a y-intercept of 1. Y-intercept is 1. The domain, well, this function is defined for all values of x. So we'll say that the domain, x is an element of the set of real numbers. And the range, you can see that values of y that are just greater than 0. Not greater than or equal to, just greater than. Okay, and a lot of these properties will hold true for any base exponential function. Now, as we start to transform these a little bit, translating left, right, up, down, reflecting, expanding, compressing, some of these properties will change, but with these basic functions, a lot of them stay the same. Okay, let's look at 5 to the x. And we can create a table of values for ourselves. I'm just going to use -1, 0, and 1. Everything else, if we did 5 squared, 25, that's off the graph. But so 5 to the power of 0, 0 law, this is 1. Whoops. 5 to the power of 1 is 5. And 5 to the power of -1, so we're reciprocating the base, we get 1 over 5. Okay, so when we graph this, we just have 3 points here, but this will be enough. -1 and 1 over 5, 0 and 1, and 1 and 5. So 1, 2, 3, 4, 5 units up. Okay, so basically the shape is identical. The difference being that it's a bit of a steeper curve. So just going to draw this in. And so we've got a steeper curve here. And it ends up looking something like that. Okay, properties, asymptote, still the x-axis, y equals 0. We've got a y-intercept of 1. So this comes from 0 law. So any base raised to the power of 0 is 1, okay, with the exception of 0. But the domain is all real numbers, and the range y is greater than 0. Okay, let's look at another example here. Our base now is 1/2. Okay, so what impact does that have on our graph? Well, again, we can create a table of values. So let's just call this x and this y. And I'll select values of x that are near the point of origin. I'm going to use -3, -2, -1, 0, 1, 2, and 3. And again, I'm going to fill this out of order. So 1/2 to the power of 0, 0 law tells us that this is 1. 1/2 to the power of 1 is 1/2. Squared is 1/4. Cubed is 1/8. Okay. Let's look at the negative exponents. So what happens if x is -1? So we have 1/2 raised to the power of -1. Negative exponent tells us to reciprocate the base. So this becomes 2/1, which is just the integer 2. The exponent becomes positive, so this becomes 2. Okay, and you can see the pattern emerge here. To the power of -2 is 4, to the power of -3 is 8. So we have 7 different points that we can plot here. Let's start with an x-coordinate of -3, gives us a y-coordinate of 8. So 1, 2, 3, 4, 5, 6, 7, and 8. X-coordinate of -2, y-coordinate of 4, 2, 3, 4. -1 and 2. Okay, we've got a common y-intercept here, 0 and 1. And then we've got 1 and 1/2, 2 and 1/4, 3 and 1/8. And here's what the graph looks like. Okay, asymptote's the same, y equals 0. Uh, we've got a y-intercept of 1. The domain remains the same, and the range remains the same. So domain is XER, range y is greater than 0. Okay, so what sort of general statement can we make about these exponential functions then? Okay, let's have a look at this. Y is equal to a to the x. The base here is a. Okay, if the base is greater than 1, so the first two examples we looked at are this scenario. We had a base of 2, we had a base of 5. We call these increasing exponential functions. Oops. Okay, so these are increasing exponential functions. Okay, so what that means is that as x gets bigger, y gets bigger and bigger and bigger. The general shape is, something like this. Okay. Now, the example we just looked at, where we had a base of 1/2, okay, so a exists between 0 and 1, 1/2 is an example of that. We call that a decreasing exponential function. decreasing exponential function. Okay, so the shape of that looks something like this. As x gets bigger, y gets closer and closer and closer to 0. Actually, I guess I have a whole space here that I can draw that out. Okay, so if a is greater than 1, we have an increasing exponential function. Still going to have a y-intercept of 1, but the function is going to look something like this. That's increasing. Okay, if a, our base, exists between 0 and 1, so for example 1/2, which is what we just looked at, this is a decreasing exponential function. So it's going to look something like this. Okay, let's look at some other what ifs. Okay, well, what if our base is 0? Okay, so we've got 0 raised to the power of x. Okay, well, if x was a negative value, okay, then think about reciprocating 0. We end up with something which is undefined. But for all other positive values of x, and including 0, 0 raised to the power of 1, 0 raised to the power of 10, all of these are 0. So graphically, what's that going to look like? Well, it's just going to look like a linear function. For any value of x, we have a y value of 0. Okay, now what I'm going to make that look like graphically, I am going to put a hollow circle at 0. Okay, 0 raised to the power of 0 is undefined, but the function's defined for every other positive value of x, and so it's going to look something like that. Okay, now as we get into logarithms, we're going to look at restrictions on bases. We cannot have a base of 0 because if you look at the graph, this does not look like an exponential function. It looks like a linear function, and it is. So we restrict the base in that manner. Okay, how about if the base is 1? Okay, same idea. Well, if we've got any value of x, the y value is still going to be 1. 1 raised to the power of 10 is 1. 1 raised to the power of 0 is 1. 1 raised to the power of negative 10 is still 1. So what is this going to look like? It's going to look like a linear function as well. Just a straight line at y equals 1. Okay, so getting a little bit ahead of ourselves, that'll be another restriction on our base. We cannot have a logarithmic function with a base of 1. Okay, how about negative 3 to the x? Okay, well, this is an interesting little experiment here. Let's do, we're going to create a couple of tables of values. So I'm just going to jot this over in the margin on the right. Let's try 0, 1, 2, and 3. So negative 3 to the power of 0 is 1. Negative 3 to the power of 1 is negative 3. Negative 3 squared is positive 9. And negative 3 cubed is negative 27. Okay, that's going to be off the graph. Okay, 0 and 1. 1 and negative 3. 2 and 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, that's very interesting. It's kind of bouncing back and forth. Positive, negative, positive, negative. Let's choose some other values of x. Let's see what happens. Just going to do another table of values. Let's try negative 1, negative 2, and negative 3. Okay, so negative 3 raised to the power of negative 1, flip the base, exponent becomes positive. We would get negative 1 over 3. Oops. We would get negative 1 over 3. Okay, flip the base. We've got negative 1 over 3 raised to the power of positive 2. This is going to be positive 1 over 9. And we would get negative 1 over 27. Okay, so if we tried to graph this, negative 1 and negative 1 over 3, something like that. Negative 2 and positive 1 over 9, something like that. Okay, so again, we've got this graph that's kind of bouncing positive, negative, positive, negative. I'm going to create one more table of values, and I hope that this kind of drives home the point that I am very subtly making. Let's say that x was, say, 1/2, okay, or 1 over 4, okay? Well, you might be thinking to yourself, okay, if our exponent is 1/2, then really what we're doing is this. Negative 3 raised to the power of 1/2 is the square root of negative 3. Okay, this is undefined. Okay, same thing with 1 over 4. That would be so negative 3 to the power of 1 over 4. These are our fractional exponents. This is the fourth root of negative 3, also undefined. We'll just fill that into our table of values, undefined, undefined. And so the whole point being here is we have a restriction on bases. We do not use negative bases because, as we're starting to see, they are undefined in an infinite number of places. Okay, so just write a little note to ourselves here. We do not use negative bases because they are undefined in an infinite number of places. Okay, and we'll revisit all of this when we actually start talking about logarithms, which will be next week. Okay, so how about some transformed exponential functions? So this is y equals 10 to the x plus 1. Okay, so our transformation here, this is the base function 10 to the x, but it's been shifted 1 unit up. Okay, so what does 10 to the x look like? Well, it's going to have a y-intercept of 1. I see these problems persist even while teaching virtually. Okay, so I'm not going to be super particular here, but this is an increasing exponential function. Looks something like that. It has a horizontal asymptote at y equals 0. If we shift this now 1 unit up, that horizontal asymptote's also going to move 1 unit up. Okay, so we'll do this transformed version in red. That y-intercept goes up 1, and the shape will be more or less the same, and it's going to look something like that. Okay. Next one. Okay, same idea here. I'll identify what the base function is as we start to work with some more complex functions. Our base function here is y equals 2 to the x. Okay, now thinking about transformations, if we replace x with x minus 2, what happens? We have a translation or a shift of 2 units to the right. Okay, so our base function remains exactly, or our base function is the same. Here's our base function in blue. And the transformed function is shifted 2 to the right. So I'm just going to move those significant points over 2 to the right. And as best I can, I will redraw this. Okay, that horizontal asymptote is unchanged. Okay, let's have a look at another one. So we've got y is equal to 3 to the negative x. Okay, so again, our base function is 3 to the x. So y is equal to 3 to the x. Okay, what happens when we replace x with negative x? We have a reflection or a flip over the y-axis. Okay, so what is that going to look like? Well, we can create a little table of values here. And if I choose 1, 2, and 3 as my values of x, then that's 3 to the power of negative 1, 3 to the power of negative 2, 3 to the power of negative 3. So this is 1 over 3, 1 over 9, 1 over 27. Okay, our base function is this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's our base function. And in red, we will flip that over the y. Okay, so the y-intercept stays the same. We're flipping that over the y. We're flipping this over the y. And the transformed function looks something like this. There we go. Okay, just a couple more here. All right. How about 2 times 1 over 3 to the x? Okay, well, again, let's start by identifying the base function as I scroll all the way back down here. So our base function is y equals 1 over 3 to the x. Now we've multiplied the base function by 2, so we can think about that as being our a value. And what does it represent? It represents vertical expansion by a factor of 2. Okay, so what does 1 over 3 to the x look like? So our base is between 0 and 1, so this is a decreasing exponential function. So it's going to look something like this. Okay, and then vertically expanding by a factor of 2. So take each of those y coordinates and double them or multiply them by 2. I'm going to do that and that. And we should end up with something like that. Okay, very, very, very similar, but with our larger values of y, we can see that the transformed version of the graph is twice as tall. Okay, and the last one here. So we've got y plus 3 is equal to 5 to the power of x minus 6. First step, let's just isolate y. So we're going to get y is equal to 5 to the x minus 6. That's our exponent. And then minus 3. Okay, what's our base function? Our base function is just 5 to the x. Okay, so base function is y equals 5 to the x. How has that been transformed? Okay, well, we've got a translation of 6 units to the right, and we've got a translation of 3 units down. So in blue, let's draw that base function y equals 5 to the x. And this is a increasing exponential function. We did this in question 2 of these notes, I believe. So it's going to look something like that. And now we want to redraw the same thing, but translating 6 units to the right and 3 units down. Okay, well, one of the things that I will do is with that translation of 3 units down, our horizontal asymptote is going to go from y equals 0 to y equals negative 3. So let's drop this. Oh, it's equally as frustrating. We will drop this to y equals negative 3. 1. Okay, and so we can take, I've only drawn in 2 significant points there, but we can shift them or translate them 6 to the right. So 1, 2, 3, 4, 5, 6, and down 3, 1, 2, 3. And same thing here, 1, 2, 3, 4, 5, 6 to the right, 1, 2, 3 down. And as we redraw that exponential function, we end up with something like that. And that is it for today. Hope everyone's well. Talk to you soon.